Hello students, today we are going to be introducing the set of natural numbers and the Peano axioms. So now we're going to be moving on from the introduction and context of real analysis into the actual coursework. So to start off, think about the very first math lesson you ever had as a child. Before equations, before fractions, before any rules at all, the very fundamental thing. You learn how to do one basic thing, which is to count, right? So simple enough. 1, 2, 3, 4, etc. It feels completely obvious, right? We feel like numbers are just a fundamental part of nature waiting for us under a rock. But if we want to build a bulletproof mathematics, we have to ask a deceptively simple question, which is, what even is a number? If you had to explain what the number 1 is to someone without using other numbers, how would you define it? In the late 1800s, mathematicians realized that if they didn't create a rock-solid foundation for counting numbers, everything built on top of them, calculus, physics, engineering, was resting on shaking assumptions. So today we step into section B of our course, which is building the number system. We leave the rules of logic behind, and we begin building math from scratch. We're going to see how a mathematician named Giuseppe Peano uses just a few simple rules to construct an infinite chain of numbers out of absolute nothingness. To build a universe of numbers, Peano realizes he didn't need an infinite list of definitions. He only needed a starting point and a mechanism to move forward. So think of it like laying down train tracks. You don't need to conjure an entire miles-long track out of thin air all at once. You just need a starting brick and a tool that can always drop down one more track section right in front of you. So Peano's very first rule is 1 is a natural number. So rule 1 is going to serve as the anchor. And other textbooks I know will use 0 and say 0 is the element of natural numbers, but we're going to go with the definition that Kenneth Ross in his textbook Elementary Analysis provides, just for the sake of some sort of, consistency. So this is our anchor point. We simply accept that a starting object exists. That's what matters. His second rule introduces our core mechanism. It says for every number there is a unique next number that follows it. And we call this the successor function. And this is labeled as S of n. So think of S as simply taking one step forward. If we start at 1, right? The next object is S of 1. We choose to give this object the name of 2. The step after that is S of 2, and we call this 3. And this goes on pretty intuitively. By using just this one simple action, we can generate a path that can actually go on forever. But just saying keep taking steps isn't enough. If you aren't careful, your train tracks might curve around and run into themselves, creating a loop that gets trapped. For example, what if the number after 2 went right back to 1? Then our numbers would just reach a cycle of 1, 2, 1, 2, 1, 2, and we would never reach 3, and infinity would collapse. So to prevent this structural trap, Peano added 2 beautiful safeguards. So the first thing he states is that 1 is never the next step for any number. So S of n, the successor function, cannot equal 1 for any number, for any n. The number 1 is the absolute beginning. Nothing can ever step backward into the starting gate. Second, he states that different numbers must have different successors. Think of this like walking down a straight path. 2 completely separate starting tracks can never merge into the exact same stepping stone. So more formally, we'll say if x does not equal y, then s of x cannot equal s of y. And what this means is if you're given two numbers, x and y, and they're different, then their successor functions cannot be the same. If 2 and 3 both led to the exact same next number, our timeline would collide and blend together. By making sure no two paths ever crash into each other, Peano guarantees that our line of numbers always branches outward, clean and straight, forever. Now we have a straight line going out to infinity, but we face one final hurdle, which is how do we make absolutely sure that this simple stepping stone chain covers all counting numbers, right? And to lock the system down, Peano introduces the most famous rule, which is called the axiom of induction. And this is going to be the fifth axiom of his set of Peano axioms. So don't let the name intimidate you. It's easiest to understand using a row of dominoes. So suppose you have an infinitely long line of dominoes. So how do you guarantee that every single domino in the universe will fall? The first thing is you have to actually knock over the first domino, right? And the second thing is you have to verify that the dominoes are close enough so that if any random domino falls, it is guaranteed to hit the next one. So now that you have these two conditions meeting, a beautiful chain reaction sweeps all the way out to infinity. This rule ensures that our simple step-by-step definition fully captures every single natural number that can possibly exist. So look at what we've accomplished. By stripping away all our preconceived notions, we've constructed the infinite universe of counting numbers using a small set of pretty straightforward rules. We've initialized our system with an anchor point at 1. We've created an unstoppable forward engine with the successor step, and we've placed guardrails to prevent loops and collisions. And then we used a domino safety net to make sure no number was left behind. So I guess we can restate this with these, even more understandable rule components, which is just the first being 1 is an element of the natural number, 2, no loopbacks, and 3, the domino rule. So this elegant framework is the foundational bedrock of all real analysis. Every time you write down an equation, add parameters, or analyze a trend, you are actually operating inside the world these simple rules created. So now that we've used our domino rule to build the numbers themselves, it's time to weaponize that exact same rule to prove massive claims across the infinite landscape. So in our next video, we're actually going to look directly at the most powerful proof engine for whole numbers, which is mathematical induction. We're going to see how knocking over just one base argument can automatically prove that a mathematical statement holds true for all numbers for eternity. So now that the foundation is laid, we can start climbing. I'll see you in the next video. Thank you.